So, dear students, our last heterocyclic moiety in unit number 3 is thiophene. So, thiophene looks like this. It's a sulfur atom in the 5-membered ring, and this is our last heterocyclic moiety. Now, here you can see that sulfur is the heteroatom, and this thiophene is a colorless liquid. It has a boiling point of around 84 degrees centigrade. Okay, it was isolated as an impurity in benzene in 1882 by Victor Mayer. Okay, it also contains pi bond, pi electrons, so it's also a pi excessive aromatic heterocyclic. Okay, now let's see the methods of preparation, MOPs of thiophene. Now first synthesis is Pal-Nor synthesis. Pal-Nor synthesis. For Pal-Nor synthesis, you require 1,4-dicarbonyl compound. For example, we have CH3, okay, we are having 1,4-dicarbonyl compound, and these 1,4-dicarbonyl compound can be treated by P2S5, phosphorus pentasulfide, and phosphorus pentasulfide is a source of sulfur. Over here, this reaction is heated up to 250 degrees centigrade, and you see the formation of a substituted pyrrole having 2 methyl groups on the 2nd and 5th position. So it's a simple cyclization process of just converting 1,4-dicarbonyl compound to the thiophene. Okay, sulfide there in this reaction also act as a dehydrating agent. It works by removing water molecule. If you take H2S as a catalyst, this reaction becomes also effective. Now the second method is Hinsberg synthesis. Hinsberg synthesis requires 1,2-dicarbonyl compound, and you react this 1,2-dicarbonyl compound with diethyl thiodiacetate. Diethyl dithioacetate. Okay, C double bond O, single bond O, single bond O, O, ET. Now if you react with this in presence of a base, that means C2H5O negative and a positive, base is required, and alcohol is used as a solvent, then we get a substituted thiophene. So we get a substituted thiophene by the Hinsberg reaction. Now the next reaction for the preparation of thiophene is Fisselman thiophene synthesis. Fisselman thiophene synthesis. In Fisselman thiophene synthesis, this reaction is a base catalyzed condensation reaction. It is a base catalyzed condensation reaction. Okay, it's a base catalyzed condensation reaction where we are reacting thioglycolic acid. Thioglycolic acid is SH CH2 C double bond O single bond R Okay, so we are reacting this with thioglycolic acid. Okay, so we are having one thioglycolic acid, and the compound we have is alpha beta acetylenic ester. Alpha beta acetylenic ester. Okay, so when we react these two compounds in presence of NaOH, because I've already told that it's a base catalyzed reaction, we get substituted thiophene. OH C double bond O single bond R1. So this is Fisselman thiophene synthesis. Okay. Now the next reaction for preparation of thiophene is, our fourth reaction is Gewalt aminothiophene synthesis. Aminothiophene synthesis. So in Gewalt aminothiophene synthesis, we will perform a base catalyzed condensation of a ketone with a beta ketonitrile. So we are having a ketone R1 C double bond O single bond CH single bond R2, and we are reacting it with a beta ketonitrile. This one is ketone and we react it with beta ketonitrile. So beta ketonitrile is N triple bond C single bond CH2 single bond C double bond O single bond OR. So we are having beta ketonitrile, These two react with each other in presence of sulfur and amine, and we get a substituted thiophene. So this is Gewalt aminothiophene synthesis for the preparation of substituted thiophene. Now there are some industrial methods as well which can be used for the preparation of thiophene. First method is from the butane. Butane is CH3 CH2 CH2 CH3. We are having a butane, and when butane is reacted with sulfur at 600 degrees centigrade, we get thiophene. We get formation of thiophene. Thiophene can also be prepared by using acetylene. So take acetylene and react it with hydrogen sulfide gas, then you also get thiophene. Okay. So the whole process over here is actually a dehydrogenation process. The hydrogen is removed. Third industrial method that you can use to prepare thiophene is by reaction with a sodium salt of dicarboxylic acid, COO negative, Na positive. It's a succinic acid, sodium succinate. This molecule is sodium succinate. Now react this sodium succinate with P2S3 phosphorus trisulfide at 200 degrees centigrade. Then you will get thiophene. So these were the method of preparations of thiophene. Now let us understand the chemical reaction. Chemical reactions. Now how does thiophene react? So the first reaction for the thiophene is protonation. So when you protonate thiophene, when you protonate thiophene, protonation can be done in the presence of acid. The acid which we are using here is H3PO4 at 90 degrees centigrade, and due to H3PO4 we get a trimer of thiophene. A trimer means 3 molecules of thiophene fuse with each other and we get thiophene as a trimer. Okay. The second reaction is oxidation. When we perform the oxidation of thiophene, when we do the thiophene by various oxidizing agents, for example nitric acid, the most common oxidizing agent used in lab. So say we are performing the oxidation by help of nitric acid. This ring will break down and we will get oxalic acid, COOH, oxalic acid, and we can also get maleic acid. Maleic acid is CHCOOH double bond CHCOOH. This is maleic acid. So oxalic acids and maleic acids are obtained. Okay. Now the next reaction to be done is electrophilic substitution. The electrophilic substitution, a wide variety of electrophilic substitution is given by thiophene. It can be given by thiophene. Now let us see you perform the nitration of thiophene. For nitration you can use several reagents. So thiophene undergoes electrophilic substitution reaction majority at C2 and we get 2-nitrothiophene, okay, as a major product. Say if you want to perform sulfonation, sulfonation can be done by pyridine SO3 complex. So sulfonation will happen and obviously it will happen at second position. You can also do the chlorosulfonation by using chlorosulfonic acid. So when you will do chlorosulfonation, you will see that SO2Cl is formed again at the second position. Now chlorination of this molecule also happens at second position, same as that happens with bromination. So this bromination also happens at second position. Same happens with iodination. So if you perform iodination, react with iodine, then the iodine is attached to the second position. You can also have this C double bond O CH3 acetyl group at the second position again by using acetylating agent, for example acetyl chloride. You can also undergo alkylation, and if you undergo alkylation, you will see that whatever the alkyl group is, it is attached to the second position. So the main electrophilic substitution reaction, the main substitution position is at position number 2 for the thiophene. Okay, so these are all the reactions. Now coming to our next reaction, which is nucleophilic substitution reaction by thiophene. Nucleophilic substitution reaction by thiophene. Now for thiophene, let's say we are having thiophene and we are having bromine at its second position, and we want to do nucleophilic substitution. So first of all, we react it with copper chloride and pyridine in presence of DMSO, which is a polar solvent. So substitution will happen. A bromine will get replaced by chlorine. You can also perform nucleophilic substitution with KNH2, okay, potassium amide in liquid NH3. NH2 will act as a nucleophile and it will give a 2 substituted product. You can also do this substitution by copper oxide Ki and CH3OH. So you will get an OCH3 group at the second position, and while performing substitution with copper cyanide and pyridine, we get substitution at the second position. So these were the nucleophilic substitution given by thiophene. Now talking about the reduction process, the reduction reactions given by thiophene. Now if you undergo reduction reactions, if you perform the reduction of thiophene, you can first do it by sodium alcohol CH3OH in presence of NH3 minus 40 degrees centigrade, and you will see that sulfur is partially reduced either at 2,3 position or at 3,4 position, along with CH3, CH2, CH2, CH2SH. This is butane thiol. These products are formed. Now if you reduce by palladium charcoal, you will get a complete reduced sulfur, which is known as tetrahydrothiophene. Now the last reaction can be done by Raney-Nickel. The reduction can be done by Raney-Nickel in presence of acetic anhydride, and the ring opening will happen and you will get CH3, CH2, CH2, CH3. That means you will get N-butane. So this completes the chemical reaction of thiophene. Now applications of thiophene. Thiophene is widely applied in many heterocyclic compounds which are commercially used as medicine belonging to the antibacterial category, anti-inflammatory, category, okay, and many more. A few examples of thiophene containing drugs are lomoxicam. Lomoxicam, it's a anisate. Pyrantel pamoate, which is an antiparasitic drug. Reltitrixate, an anti-cancer drug. Cephalothene, it's an antimicrobial. Okay. Ticlopidine, which is a platelet aggregation inhibitor. So this was all about thiophene. And now we arrive to a very important topic which is related to both pyrrole, thiophene and furon. We want to know what is the order of aromaticity. What is the order of aromaticity between pyrrole, thiophene and furon? Now we want to see what is the aromaticity order, which one is most aromatic and which one is the least aromatic. Now you know that to become aromatic, for a compound to become aromatic, the following condition must be satisfied. Number 1, the compound should be cyclic. Number 2, it should be planar. Number 3, it must be conjugated. And number 4, it must contain 4n plus 2 number of pi electron, where n is integer. Any molecule who does not follow any of the 4 points will not be a aromatic compound. So in that case, you see that all thiophene, furon and pyrrole, they all are aromatic, because in pyrrole you will see there are 3 pairs of pi electron. That means 6 pi electrons are there. In furon also 6 pi electrons are at the conjugated system. Okay, 6 pi electron in furon is there, and it's also aromatic. And same as that happens with sulfur, it also has in thiophene, it also has 6 pi electron with them. Now, because all the 3 are aromatic, we just want to know which one is more aromatic and which one is less. Okay, so this thing depends on the electronegativity of the heteroatom. If we see, we will find that the highest electronegativity, if we see the order of electronegativity of the atom, we see that oxygen has highest electronegativity, followed by nitrogen and followed by sulfur. Means oxygen is highest electronegative atom, then lesser electronegativity is of nitrogen, and the least electronegativity is of sulfur. Now electronegativity has an important contribution where this heteroatom contributes its electron to the pi system. If the electronegativity is high, chances or you can say the propensity of any atom to contribute its electron in the pi system for aromaticity will be low. So you can say that the aromaticity will be low in this case. Whereas if the electronegativity is low, the propensity of an atom to contribute its electron in the ring system and make a 4n plus 2 pi arrangement, it will be high. That means the aromaticity will be high. So as you can see that oxygen has highest electronegativity followed by nitrogen and sulfur. It means the one which is least electronegative will be highest aromatic. So hence thiophene is most aromatic. Its aromaticity will be the most, followed by pyrrole, which comes after thiophene in terms of aromaticity, and then followed by furan, which is least aromatic among all of them. So please remember that aromaticity will depend upon the electronegative character of this heteroatom. The one which is having the highest electronegative character, which will have a lower propensity to contribute its electron, because conjugated system creates only when these electrons are shared to the pi electron system, to the conjugated system. If they do not give the electrons in the conjugation, their aromatic character will decrease. So hence the aromatic character follows the order. The highest aromaticity is of thiophene, then it is of pyrrole, and then it is of furan. So I hope you all have understood what are the properties of different heterocyclic pyrrole, furan and thiophene are, what are their method of preparation and their aromaticity order. So this completes our unit number 3rd, and in unit number 4 we are going to learn about more heterocyclic, having more than one heteroatom in the ring, and those heterocyclic which are of much more importance in medicinal chemistry. Thank you so much. Dear students, I hope you have learned very well about unit number 3rd, the basics of different heterocyclic compounds. You have learned how to give their names as per IUPAC nomenclature. I hope you have understood the basic idea of how heterocyclic compounds are prepared in the laboratory and how they behave chemically in different chemical environments. So in our next unit, we will going to study some more complex heterocyclic compound. That will be our unit number 4. Till then, thank you so much.